Hey all, I've got one today that I bet you didn't think was going to be coming up in linear algebra. So I'm sure that at some point in a chemistry or maybe a biology or physics class or a statistics class, somebody gave you a bunch of data and had you plot it in Excel and then run a trend line through it, right? That's a relatively common data analysis task. And today we're going to learn in linear algebra how that actually gets done. So I'm going to play with this by example, and then I'm going to give you a more serious thing. But I bet once we're done with the example, you'll be able to figure out how the more serious thing works. So I have this little toy set up, right? I have three data points. My data points are 0, 6, 1, 0, and 2, 0. So if you're paying attention, I'm hoping that you're looking at those and seeing, hey, Joe, those aren't on a line. You're not going to be able to do this. And that's correct. I'm not going to be able to do this. I am going to be able to come up with an approximation, a best line, if you will, right? We sometimes call the least squares regression line the line of best fit. And today we're going to actually figure out what we actually meant by best in that case. So I've got here my 3 points, and my goal is going to be to create a line a bit like this one. So I think that line's probably going to look something like that. At the end here, we'll be able to plot a line and we'll be able to check it against this one that I've made in my head, right? Humans are actually pretty good at drawing least squares lines, which is weird. So let's show the mechanics of how we're going to do this. The first thing I'm going to do is I'm going to write down what a line looks like. I'm going to use a slightly different form than you're probably used to. So instead of writing y equals mx plus b, just because those letters are sometimes used in here, I'm going to write c plus d uh, t equals b. Okay. This is just going to be our notation for writing a line. Same as it always was. I'm just picking these letters so that I don't mix them up. So what I'm thinking about these points as this is the kind of t-axis and the b-axis, right? Really, they're the x and y-axis. I'm just thinking of this relationship as between t's and b's, right? So what I'm going to do is I'm going to go ahead and think about my 3 points in those terms. So I'm going to have c plus the t for this one is going to be 0. So I've got d times 0 is going to be 6. I'm going to have c plus d times 1 is 0. And c plus d times 2 is also equal to 0. Then I'm going to rewrite this in terms of a matrix because big surprise, we're in linear algebra, we use matrices. So I'm going to go ahead and do that. So if I do that, I'm looking at a matrix that looks like 1, 1, 1, 0, 1, 2 times the vector CD is going to equal this new vector 6, 0, 0. Okay, these matrices that I make here are generally going to be tall, skinny guys, right? There's going to be more data than there are constraints on my line, right? So my line's got the kind of two things that make a line go, right? An intercept and a slope, and I've got three data points. If I had 37 data points, they'd be all just stacked down here, right? It'd be a nice long list, but it'd still be a list that I could handle, right? Okay, so here's my goal. I'm going to think back to general projection, and I'm going to think to myself, hey, in order to actually be on a line, I would have to be able to solve this equation, right? I could put this in an augmented matrix and row reduce it, demonstrate that's not going to work. Actually, let me do that. I'm going to pause the video quick. Okay, so when I did that, I got this. So I put in my matrix here, right? Remember, there's kind of an augment there. I row reduced it and I got this guy. That last equation reads 0 equals 1. So this essentially just didn't work, right? Which I knew it wasn't going to work because this line doesn't go through those 3 points. There's not going to be a way for me to make a line through these points, right? To be through the bottom two, it'd have to be horizontal. To be through the upper one and either of the bottom ones, it can't be horizontal. This just isn't going to be a thing. So what I need to do is I need to say, all right, look, I really wish that 600 were a set of numbers, right? A vector that made this problem solvable, right? So what I need to do is I really want this vector to be in the column space of my matrix. So I'm going to call this matrix A for a minute. Actually, let me write that in a different color so we don't get ourselves messed up. I'm going to think about that matrix as a matrix A. I'm going to think about this matrix as a vector B. And I'm going to think about this as a vector X. The kick is I know right now that the equations here, right, the or the matrix equation, AX equals B, right now as it stands, is not solvable. And I know it's not solvable because B isn't in the column space of A. So what I'm going to do is I'm going to do a little settling, right? So what I'm going to do is I'm going to project B onto the column space of A. And then I'm going to solve that equation. So that's going to give me an equation like AX hat equals B parallel. Remember in that earlier lecture where I told you that X hat was going to come back to us? Well, here he is, right? So what I know is that if I'm trying to solve something like this, I can go ahead and project B parallel, right? So if I actually do that projection, right, I'm going to go get out my formula from before. So I'm going to project, right? And I'm actually just going to drop that A here. So I'm going to just go get my projection formula, right? So I'm just going back here to my more general projections. I'm going to grab this projection formula here. That's going to say that X hat is A transpose A's inverse done to A transpose B. And that's all this is. Right now, I can just go ahead and crank on this. I just need to take this matrix A and put it into this formula that's going to go ahead and give me X hat. So X hat in my case is going to be, I need to take my matrix A and transpose it. So that's going to be 1, 1, 1, 0, 1, 2 times my matrix A, 1, 1, 1, 1, 2, or sorry, 0, 1, 2. This whole thing inverted times 1, 1, 1, 0, 1, 2. Oops, I didn't need that parenthesis there. Times my vector B 6, 0, 0. And we can go ahead and just do this, right? So we can do this multiplication. It's going to be a little annoying, but it's not really that bad. So I'm going to do this one by hand just once, right? So in order to do this part, I have to kind of pick this column up, twist it, drop it on. So I'm going to get 3 out of that. If I pick this up and drop it on these guys, I'm going to get 1 plus 2 is also 3. Then I'm going to take this guy, I'm going to pick it up, I'm going to drop it on, I'm going to get a 3 again. I'm going to pick this guy up, drop it on. I'm going to get 1 plus 4 is 5. So I need to invert that matrix there. And then I'm going to need to multiply by this crap. And that multiplication I can just do right now. That's going to give me the vector 6, 0. Okay, so I need to invert this matrix. I'm just going to use that 2 by 2 flip trick, right? So I need 1 over 15 minus 9 is 6 times my matrix here is going to be, I need to swap the places of the 5 and 3. I need to put negatives on the 3's. And then I need to multiply this by 6, 0. Good news here. I can kind of do this out of order, so I can womp this 6 against that 6 and be left with a 1. So then I can go ahead and just do this multiplication. So I'm going to get the vector 5, negative 3. Now, this probably isn't what you're going to want to do by hand. I'll show you the Desmos trick here in a second. So I got this guy. What is that? Well, that's the X hat, which is my best guess for X that I couldn't solve for. So that X hat is my C and D. So this means that my line is, let's see, 5 minus 3t equals b. That's my kind of best bet on this line. So let me plot that in Desmos and we'll take a look. Okay, so here I've got my data points and I'm just plotting line was 5 minus 3x. There's my line. Oh, and we notice that something's a little bit different than what I guessed. You guys see that? I guessed that this was actually just going to go through the point 0.06, and it just doesn't quite. It's pretty close, but it doesn't quite go through it. So I didn't quite get this right, but I'm not bad. Like looking at those, they look pretty similar. Desmos calculator wise, if you want to cram this in, right? I put in my matrix A, I put in my matrix B. I just have to in here type my formula. So I'm just double checking my arithmetic, right? So I need A transpose A inverted times A transpose times my vector B. Yep. I got 5, -3. Great. That's correct. If I did this in Excel, that's actually also what I'd get. Sorry, I didn't queue that up, so I don't have it here. But here we are, done. That's our line. Great, easy peasy. What was the trick here? Well, there's actually only a little bit. So the little bit here, like the actual trick that I need, is essentially just two things. Thing one, I need to recall that thing about what x hat is. Thing two, I need to figure out how to write down what it means to be on a line. So what does it mean for those points to be on a line? Now, this is clever. It's easy to forget how this works. It's really easy to follow this lecture and really, really hard to reproduce it later. So I really encourage you to like get this out, pause this video, maybe wait a couple hours, go back, try to do this without watching the video, and then double check that I did it, that you did everything I did. Because it's not super easy. All right, one last thing. Let's talk about what it actually meant here. So I'm going to go grab my picture again. So I'm grabbing my picture from before. I'm going to place that down right here. And then I'm going to do one more thing. I'm going to grab my Desmos matrix calculator here. So this guy. And I'm going to write down, well, what does it mean to take this stuff? And if I do A to it, I get B parallel. So this is 5, 2, -1 is B parallel, right? So let me pause this and fiddle with my graph. All right, so I've done just a little bit of off-camera mining, right? And I put my new P's, right? Which are 0, 5, 1, 2, and 2, -1. Where did I get those? Well, I went in here to B parallel. So let me just swap that picture out quick. So here's one bit of picture, and here's my other bit. So what I did was I looked at B parallel, right? So my original B was 600, right? My B parallel was 5, 2, -1. And what I did here is I swapped out. So the red points are the ones that went with my original 600. Then the green points are the ones where I swapped out the y coordinates for what was in my B parallel. So notice that now those 3 points are on a line. And the thing I minimized here is I had the column space of A looked something like this, right? And my vector B, let's see, vector B stuck up like this. It wasn't in the column space. So I decomposed it into a green piece in the column space and a red piece that sticks straight out of the column space, right? So that red bit, that guy is B perpendicular, which we're not using. The purple bit was my original B, and the green bit, that's my B parallel, right? That's the one that's actually in the column space. So what's the least squares part here? Well, I made this green bit so that it was as close as possible in the column space to the B bit. In other words, what I did was I projected, and projection minimizes the length of B perpendicular. Like that's essentially what projection does. So if it minimizes the length of B perpendicular, well, what the hell is B perpendicular? Well, remember, B perpendicular is B minus B parallel, right? In my picture, B perpendicular is right here. That's that distance there, this distance here, and this distance here. I made those as small. I made the sum of those distances squared as small as possible, right? These guys are the kind of error vector, right? This is how far off was I from being on a line, right? So if this is, in this case, this is a length of one, this is really a length of minus one, right? This is a length of two, and this is also a length of one. And so my magnitude of B perpendicular, right, is the square root of 1 squared plus 2 squared plus 1 squared. So this is a magnitude of 2, right? That's, no, it's not. I can do math. Sorry, my bad. So this inner bit is square root of 6. So I got square root of 6 here. The square root of 6 is the shortest distance that I can say B is from the column space of A, right? So this is why we call it least squares. We're lessening squares, right? This is the least squared sum I can make. That's why we call it least squares. All right. Thanks, guys. I'll give you a more detail or a more general version of this in a second, but I really hope this is plenty to get you started.